lecture videos and lecture notes of each week. Okay, so week 1 content is first thing is field of complex numbers, conjugation and absolute value, and topology of complex plane. Okay, so what would be my plan for each week? Okay, so plan for week and like so it is a 2-hour problem solving session. So what I will do, first hour I will briefly recall the contents. Okay, what is there in that contents, and then again for 1 hour we'll do the problem solving session, and this problem solving session will be based upon the previous year course assignment. Okay, each week. Okay, so let us start with this, just recalling this, what is field of complex numbers. Okay, so now the first question is, what is field? Okay, so I mean the field is a set with two operations which satisfy some properties. Okay, so I hope everyone will recall those things. Okay, so now what is the problem with field of this real numbers? Okay, why do we need even field of complex numbers? Okay, so like as we know that this R is a field with usual addition and multiplication. So I will not go that much into the basic, because our aim is to solve the problems, like problem solving. These things I request everyone to go through the basics from the lecture videos and lecture notes, and whatever the books are there in the references, please go through those books. Okay, okay, so now if you take any real number, okay, is x square is positive, and if you add any positive number to this one, this is again going to be positive. Let us say for x square plus 1 is positive. Okay, so this is greater than equals to 0. Now the question is, if you take x square plus 1 equals to 0, this has no solution in R. What do you mean by no solution in R? Means there does not exist any R x, there does not exist any x in R such that x square plus 1 equals to 0. Okay, so we want to overcome this drawback. Okay, so field of complex number will be addressing this problem. Okay, so let us look at the definition. Okay, so basically field of complex number, let us see C, because later we will denote it by C only. Okay, is a field which contains R as a subfield which contains R as a subfield and root I to the polynomial x square plus 1. Okay, furthermore so there does not exist any proper subfield of C containing containing R and I. Okay, so in this sense it is maximal. Okay, so now so we have defined what we mean by a field of complex number. So the definition basically is a solution of this problem. Okay, that we want that root of these things will be in our field. Now the question is whether such fields even exist or not. Okay, so we have two questions. First thing is existence, and the second thing is uniqueness. So uniqueness in the sense that up to isomorphism. I will mention what do we mean by isomorphism here. So as a vector space there will be isomorph. Okay, so for existence if we see, so consider this set Rx is equals to, so this is basically the collection of all polynomials. So A naught a dx to the power d such that ai belongs to R and d is, so d is non-negative integer. Okay, now again these are the basic facts and you can go through any book on algebra. So is a commutative ring with identity. Okay, identity means with respect to addition. Okay, is a commutative ring okay. So now let P belongs to Rx be any non-constant polynomial. Okay, so now my question is, does there exist any Q such that Px dot Qx is equals to 1? So what would be the answer? Can anyone tell me? Anyone? Yeah, so as Swami said that it is only possible for constants. Okay, that is right, because if you have P as a non-constant polynomial, suppose can Qx be can Qx be a constant polynomial? Again, that is not possible, so Qx has to be non-constant. So we know that degree of these Px into Qx will be equals to degree of Px plus degree of Qx. So if there exists any Q, this will contradict this thing. Okay, so this thing is not possible, means non-constant polynomials are not invertible. Okay, so in fact thing is x square plus 1 is not invertible. So now this ideal so this is non-trivial. Okay, so now what we will do is okay, so now what we will do is we will define C as this quotient only. Okay, and this one can check that it is a field and all the properties one can check. And also if you go through the notes, so I will again say that we need to encounter these two problems, existence and uniqueness. Okay, now if you go through the notes of this week's lecture, you have found that this is C is unique. Okay, so now the work is done. Okay, we have a field of complex numbers. Okay, so what we are going to do is we will define it as formally as z is equals to, because this you will see, if this element you will see, this will be nothing but p of I only. Okay, I will again mention that please go through the notes of lecture notes of this thing. Okay, so now we will define C as z is equals to x plus iy such that x belongs to R and y belongs to R. Okay, so this is the thing now. So this is your set of complex numbers. And you can say that set of complex numbers, later on you can say that it is a field over R, again vector space over R. Okay, all these things you can talk about field of complex numbers. Okay, now we know that now as I said, we have to talk about conjugation and absolute value. So this everyone know, these are all basic things. Okay, like if you take z belongs to C and you want to consider z bar, which is nothing but x minus iy, so this is nothing but a reflection about x-axis. Okay, so your x is here, geometrically this is the meaning. Okay, similarly if you want to talk about mod z, so mod z is nothing but under root x square plus y square. So mod z is nothing but, suppose your z is here. Okay, this is nothing but the distance from the origin, so this is the vector. Okay, and you want to measure this quantity, so this is nothing but x square plus y square. So here you can observe that mod z is equals to x square plus y square, which is nothing but z into z bar. Okay, so these are all related to this thing. Okay, so I will again recall what we have done. So this is related to what do we mean by field of complex number and why do we even need such kind of field. Okay, so I will again mention that please go through the lecture notes. lecture notes and lecture videos. Okay, you can find the details there. Okay, so now with this what we can do now, with this modulus value we can define a metric on this one. So D such that C cross C to, let us say, R plus, so this is R plus union 0. Okay, so D of Z comma W is nothing but mod of Z minus W, and one can check that this is in fact a metric. Okay, so this C comma D is a metric space. Okay, now after defining the metric, what we do, we study about, so I'll request everyone to please go through these concepts, like open ball. Second thing is closed ball. So I'm just recalling what is there in the week 1 content. Okay, all these things you can go through the books, lecture notes and lecture videos. Okay, so now we will define the open set. Open ball, everyone know open set, that for each point there exists a ball which is contained in that set. I mean, every point is an interior point. Open set. Now we will define the closed set. So set is closed if C minus that set is open. Okay, fifth one is limit point. Concept of limit point, and then we can define 6. Again we can, via limit point, again we can define closed set, that a set is closed if and only if it contains all of its limit points. Okay, now one can, so these are the third topic, like topology of complex plane. Okay, these are the content of the third topic, topology of complex plane. Now again we will study our properties of open sets, like whether its union is open, intersection is open, those kind of thing. Again, property of closed sets. Okay, again sequence. Obviously sequence are very important once you are studying about the topology, because the way sequence is converging in a space, that basically describe the topology of that space. Series of complex numbers and algebra of it. So what do you mean algebra of it? It means that if Zn tends to A, Wn tends to B, then Zn plus Wn tends to A plus B, those kind of thing. Okay, now the two important things, compactness and connectedness. Okay, so these all things are basic definitions, and one should know the properties of it. When a domain in C is connected, what are the characterizations? Like in R, connected set is an interval only. Compactness, when a space is compactness, we have the close and boundedness property. So those things one should know. Okay, so what else? Let me see. Yeah, so we'll directly move towards the some problem. So assignment problems. Okay, so first thing is nothing, just we have to do the calculations only. So 1 plus 2i and 1 minus, I should write iota root 2, but okay. And we have to find what is the imaginary part of z. So again one has to solve this one. So this is nothing but 1. So this will be a square minus b square. Okay, so once you do a square minus b square, I square will be minus 1. So this will be, so this will contain only the real part, isn't it? So this imaginary part will be 0. Is it okay? Like if you do this one, 1 square minus, so this will be under root 2i square. So this will be 1 minus, this will be 2, and this will be I square. So 2i square, this will be again minus 1. So 1 plus 2, so this will be 3. So there is no imaginary part. Okay. Now the second question is, yeah, so I would like to remind that these assignment problems are from the previous year. Okay. So z is equals to minus 1 plus iota root 5 by 2 whole square. Okay, so this we need to calculate. But what we need to so real part of z. Okay, so for the real part we only worry about the real part of this one. So this will be nothing but just you square it, and so this will be 1. Now again this is square, and then again it will be minus 2ab. That we don't care because that will come into the imaginary part. Okay, so a square plus, so this will be b square, so 5i square. Okay, and this will be always 4. So this is nothing but 1 minus 5 upon 4. This will be minus 1. So answer is minus 1. These are just basic thing because we are only in the week 1 assignment. Okay, now again what is z is equals to I to the power 7. Okay, so now, so if z is equals to I to the power 7, what will be imaginary part of z bar? Okay, okay, so as we know that imaginary part of z, and what is the relation between imaginary part of z bar? What should be there?
A negative sign.
Yeah. So what would be the imaginary part of z? Yeah, so it is I to the power 7. So as we know, I square equals to minus 1. So again I square will be 1. So I to the power 4. Okay, now again I to the power 6 will be minus 1. So again I to the power 7 will be I. So I to the power 7 is minus I. Okay, so imaginary part is minus 1. Now, so imaginary part of z is minus 1. So imaginary part of z bar is 1. Okay,
Excuse me, sir.
yeah.
So we are finding that the same questions are there in our assignment also. So it's the very same set of questions this year also.
Yeah, questions might be the same, or maybe they will be on the same pattern. Okay, so we are just solving the previous year assignment. And in fact, this is just a week one, so there will not be that much difficulty in the questions. So anyhow, we will move towards the next question. So next question is 2 plus 3i. So 2 plus 3 iota modulus square, we need to find it out. So as I said, what would be the modulus square? It will be z into z bar. So 2 plus 3i into 2 minus 3i. Okay. So this is nothing but 4 minus 9i square. Again, so this will be 13. Okay, fine. Now let us look at this question. Okay, so suppose you have a metric space X D, okay, is a metric space. Okay, now if it suppose there exists another metric on X, so we say that this metric are same or induces the same topology, or they are equivalent if every ball, I mean every open set in this metric space is also open set in this metric space, and every open set in this metric space is also an open set in this metric space. Is it clear? Basically it means that if you take the identity mapping from xd to xd1, this is nothing but this is a homeomorphism. Is it clear to everyone? When this d is equivalent to d1. So d is equivalent to d1 means they will induce the same topology. Okay, it means that if you have an open set in this metric space, that will be open in this metric space, and if you have an open set in this metric space, that will again be an open set in this metric space. Okay, so which means that identity map is nothing but a homeomorphism. Okay, so let us take d1 of, let us define d1 of x comma y is equals to, wait a minute, so this let us define as d of x comma y plus 1 plus d of x comma y. Okay, now the question is whether d is equivalent to d1. Okay, so this is the question. So what we'll do, of course I need to mention one thing. So let x belongs to x, so a ball around x of radius, let us say r, is nothing but y belongs to x, such that, so if you are talking about metric space D, so d of x comma y is less than r, so this is with respect to d, and with respect to d1 it is y belongs to x such that d1 of x comma y is less than r. Okay, so let us take, let u let u be open in x comma d. What does it mean? Like if you take any x belongs to u, there exists r greater than 0 such that this ball x comma epsilon is contained in u, isn't it? Okay, now you take r dash is equals to r upon 1 plus r. Okay, and you consider with d dash. So this is nothing but y belongs to x such that d dash of x comma y is less than r dash. So we have to see that whether this is contained in U or not. Okay, so what is this basically? Oh, wait a minute. So this would be D1. So this is D1. Okay, so we have to see whether this thing is contained in this one or not. Okay, so now D1 of x comma y is what? D of x comma y plus 1 plus d of x comma y, okay, which is less than r dash, and r dash is nothing but r plus 1 by r, and this will give you d of x comma y is less than r. Okay, means this implies y belongs to bd xr. Okay, this would be, so this would be r. Okay, so this implies bd of x belongs y belongs to this one, and hence this will be a subset of u. Okay, so this implies bd1 at x with radius r dash is subset of u. Okay, so u is open in x comma d1, and similarly you can prove for others. Give the proof for other part. Okay, okay, so this question is done. Is it clear to everyone? Any doubt? Anyone? Okay, so I will repeat it. Okay, so suppose you have a set X. Okay, you have defined two metric D and D1 on X such that X comma D is a metric space and X comma D1 is again a metric space. We say that these two metric space are equivalent or they induce the same topology. If you take an open set in this one U, that will be that will again be an open set in this one, and if you take any open set in this one, that will be open in this one. Okay, so fine. Now whenever X comma D is a metric space, if you define a metric like this D1 is going to be equivalent to this one, X comma D, means the topology will be the same. Okay, topology topology is same means that if you take any sequence Zn in X, okay, so if Zn converges to Z, okay, in this topology, then Zn converges to Z in this topology also. Okay, so this is the meaning of being the same topology. Okay, having the same topology. Okay, now suppose let U be open in X comma D. Okay, it means that if you take any point X belongs to U, there exists R such that this ball will be contained in U. Okay, now you take a radius this one. Okay, and you consider a ball centered at X, radius R dash in this metric D1. This will be nothing but this set. Now what is this set? So this Y will be in X such that D1 of X comma Y is less than R dash, which means this one. And from this one you will get this one, that D of X comma Y is less than R. It means that Y belongs to this one. okay, this thing, and this thing is contained in U, okay, so it means y belongs to U, okay, and this will hold for any y, so this whole thing will be contained in U, so U is open in, okay, so U is open in this matrix. Is it clear? Any doubt? Okay. Okay, so this is there. Now the next question. Okay, so if we talk about, this is just a basic fact and you can go through any book. I will just recall. So suppose f says that x comma d1 to y comma d2 be so let be a continuous function. Okay, so the suppose u is open in x comma d1, okay, open. Can we say that f of u is open in x comma d2? No. Yeah, so the answer is no. Okay, and one can construct a lot of examples. So now the next option is, obviously, suppose k is compact in this one, so k is compact in y comma d2. So can we say that f inverse k is again compact? Can we say this thing? Yeah, exactly. So not necessarily. Why? So this is true. Okay, so this is true if x is compact, because k is already closed. Okay, so f inverse k will be closed in x. Now if x itself is compact, then its closed subsets are, yeah, exactly, it is compact. Yeah, now if k is compact in, so these are just the topology of the complex plane, which you should know once we will go into the function theory in complex plane. Okay, so if k is compact in x comma d1, then f of k is compact. So this is true. This is the well-known fact. Okay. Yeah. Now this thing. So if x comma d1 is complete, then y comma d2 is complete. Is it true? So it means that if you have a continuous function between two metric space, if the domain space is complete, can we say that the codomain space or the range space or the target domain is complete? Yeah, so some comments are there. Let me just check. So what is the answer? X such that 0 comma 1 to 0 comma 1. Yeah, exactly. Okay. So for continuous, it is easy to construct example. Now suppose if I change f is a homeomorphism. F is a homeomorphism. Suppose. Then is it true? Any other answer? Suppose f is homeomorphism and x is complete, then y is complete. Is it true? No. Any example? I'm just reading the comments here. So any example? Yeah, so R and 0, 1 are homeomorphic, but they are not. So R is complete, but 0, 1 is not complete. In fact, uh, you take R and minus pi by 2 to pi by 2, and you take the principal branch of tan inverse. Okay. So this is the basic fact. Okay. Now what is the next thing? Next question is.
Excuse me, sir.
Yes.
Can you explain the first part by giving some example? First part of the question.
This thing?
Which one?
Which first part? Okay, means image of open set is open. This you want?
Yes.
Okay, I mean you can take. So let us take fx is equals to. So f such that you take f such that r to r, okay, and you take fx is equals to x square. So this is continuous, okay. You take an open set minus 1 comma 1 in R, okay. Now its image will be 0 comma 1, okay. Now this is open, but this is not open. Is it clear, Varsa?
Yes, got it.
Okay. I mean you can construct lot of examples. In fact, if you know the definition of continuous function, it says that inverse image of every open set is open. If inverse image of every open set is open, then that function is continuous. And in fact, if that function is a homeomorphism, means its inverse is also continuous. So suppose if I'm saying function's inverse is continuous, it means that function maps open set to open set, okay. So this thing is true if your f is a homeomorphism, okay, because in that case f inverse is continuous. Yeah, what S saw me, if graph of fs has U shape, then we can, yeah, exactly. Okay, so we'll move towards the next problem. So now this is a very important question, so I will write it down. So suppose f is a finite set. Right. So suppose f subset of C is finite. Okay. Okay, better I should write. Okay, so let me explain that. So whenever I say a set is countable, I mean that whenever I say set is countable, I mean that either it is finite or it is countably infinite. Okay, and whenever I say uncountable, that will be infinite and uncountable. So suppose if you have a set F subset of C, or you can also say R2, because here we will consider C and R2 as a, so C and R2 has the same topology, we know. So taking F subset of C and R2 is same. If we are looking for looking it as a topological space or metric space. Okay, so let let F subset of C be countable. Okay, now what can we say about C minus F? Is connected. What can we say about this one? For open set connectedness is same as path connected. Thus removing finite point is remove path connected. Same if set is countable. Okay, so by removing finitely many points, it is easy to see. But suppose if your set is countable, what would be the proper explanation for this thing that it is connected? Yeah, one thing is right, that for open set in C, connectedness and path connectedness are equivalent. Okay, so if you want to check connectedness, you just check path connectedness. So path connectedness means for any 2 points there is a path. Any idea how to prove? Like suppose if I say R2 minus Q cross Q. Okay, so this is again going to be connected. Okay, any idea? I mean, these are the well-known results. I mean, if you see this thing, what is this thing? What would be this set? So it will be something like x comma y. Okay, so either x comma y both are irrational. Okay, or if x is irrational, y is rational. Okay, x is rational and y is irrational. Okay, now these are the only 3 possibilities. Okay, so if you take any x1 comma y1 and x2 comma y2, like this is like you can picturize it nicely. Okay, now suppose you have 2 points x1 and this is x1 comma y1 and x2 comma y2. Okay, so now you can, this x1 y1 and x2 y2 will have these possibilities only. Okay, fine. So suppose if x1 is irrational. Okay, is it clear? So suppose if x1 is irrational and y1 is rational, then how do we construct a path from here to here? Any idea? Anyone? This is just a discussion. You can share your view on this one. So suppose x1 is irrational and y1 is rational. Yeah, so he said just go along y1. So what you do, you go along like this. Okay, you go along like this. Okay, so all these coordinates, whatever the points you will be here, this x1 will be again irrational. So this line will belong to r2 minus q cross q. Okay, now again you have to check what is x2 and y2. Okay, so now suppose you go like this. Okay, and suppose if x2 is now suppose is x2 is rational and y2 is irrational. Okay, so if y2 is irrational, you can just go like this. Okay, so this will be your path from x1 y1 to x2 y2, isn't it? Now again, if x2 is again irrational and y2 is rational, then what we will do? Anyone? So I am saying that x1, so now suppose x2 is irrational and y2 is rational, then what we will do? Any idea?
This will be vertical line.
Yeah, exactly. Sorry, what? From where?
At the point x2,
Mhm.
y2, there will be a vertical line.
Mhm.
So there is no path a path between x1 y1 and x2 y.
Why there will be no path? So here we are taking as, let me write it down, x1 is irrational, y1 is rational, and again x2 is irrational and y2 is again rational. Okay, so what we need to do in this case? Any idea? Anyone else? Swami, travel along x2. Now again, if you travel along x2, then okay, so you want to travel like this. So all the points here, so y is rational, okay, and x2 is also rational. Okay, so in this case, like suppose if you travel like this, x1 irrational, y1 is rational. If you travel like this vertical line, okay, all these points belongs to r2 minus q cross q, isn't it? Because all these coordinates x1 will be the same, only y1 is changing. Okay, now from here if you go like this, okay, so at this point you are having some coordinate of y1. Okay, we don't know whether y1 is rational or irrational. Okay, here we don't know. Okay, now if you travel like this, all these points here, x will change, y will be the same. Okay, so this is your y2, this is your y1, and this is your y2. Okay, so what you have to do is, if y2 is rational, okay, and once y2 is rational, if you move like this, this will not be the path which will be contained in this one. Okay, so this is the problem. If, so everyone understand this one? Now in the earlier case what we are doing, that was working, but in this case it is not working, because since y2 is rational, if we move like this y2 is rational, so this x2 always has to be irrational. Yeah, always has to be irrational. But in this way, from here to here, x2 will be rational also. So this path will not work. This path will not always be contained in this r2 minus q cross q. Then what should we do in this case? Any idea? Any idea? So what we can do is, we will move from x1 comma y1. Okay, you take x1 comma y1. Okay, now you take any other point x3 comma y3, such that x3 will be rational, okay, and y3 will be irrational. Now from, okay, so let us take any point x3 comma y3 such that x3 is rational, y3 is irrational. So from here to here we have a path. Okay, let us say this is p, q and r. So from p to r we have a path, we proved earlier, isn't it? Okay, now again from r to q we again have a path, isn't it? The same path going by the vertical and horizontal, because again this is rational and this is irrational. Is it clear?
Yes.
Okay, so now combining these two paths, we will be having p to r, then r to q. So we are done. Okay, so this is the geometric intuition how this is path connected. So I hope it is clear. Is it clear? Anyone? Swami, is it clear to you? Okay, anyhow, one can think on this one later and one can ask me. Okay, so if you have any problem in this one, just let me know, or in the next class also you can ask. So this is the way how we prove the connectedness or path connectedness of this R2 minus Q cross Q. So this is a geometric intuition for that one. Okay, let me see other problems. Yeah, these things are. Now suppose if I have to prove that just wait a minute. Okay, now suppose if I have to prove that unit circle is connected, how would I prove? Any idea? If I have to prove that unit circle is connected, yeah, if a set is path connected, then it is connected. But how do we prove as a function theoretic approach? Like whatever the knowledge you are having. So you can define a map from interval to the unit circle, e to the power iota theta. Theta will vary from your principal branch of the argument, and you will get the unit circle. Now again, and this map will be a homeomorphism. You can define it as a homeomorphism. So it will map connected set to connected set. Okay. So this is the way to attack this kind of problems. Okay. Okay. Now the thing is, I think this is it, and I don't have any other problem. This is it for the week 1 assignment, because we don't have too much problems and the toughness of the problem is not that much, so it did not take that much time. So any doubt, if anyone's having, one can ask. Please let me know if anyone is having any doubt. Anyone is having doubt? Otherwise, I will close the session and we'll meet next week. Yes, Swami, anything? Okay. Yeah, one more thing I would like to say, that I will not entertain any question which will be from the present assignment, okay, because that is not permissible for us to do so. So can we define any total order on complex? So what do you mean by total order? So you have to say that you want to define an ordering. So you want to compare two complex numbers. I mean, we don't have such thing, comparing two complex numbers. Like if you want to say z is less than w, we don't have such comparison in the imaginary unit. Okay. So we want to ask about this dictionary order. Dictionary order relation. Okay, so dictionary order relation is for, I mean, once you define the dictionary order, you're talking about dictionary order topology. Means you want to change the topology of C, is it? I mean that you can always, I mean like if you see the order topology on R cross R, and if you see the what are the basis collections of all open intervals of the form like A cross B comma C cross D for A is less than C, and if A is equals to C, then you will check the ordering of B and D. But this you can do in R cross R. Now what would be about, so R cross R is nothing but R2. If you see R2, if you see complex plane C as R2, then you can talk about these kind of things. Dictionary order. It means that dictionary order topology, if you are defining, so its basis is the collection of all open intervals of the form. So A cross B comma C cross D for A is less than C, and for when A is equals to C, you will see the B less than D. So that is dictionary order. So if you see complex plane as R2, this you can do always. This is on R cross R only. I hope this answers your question. I don't know. Swami, anything? Okay, you just think about it. You can ask this again in the next week assignment. Yeah, sure. Okay, so thank you everyone. I will close the session. We'll meet in the next session, same timings, Sunday 7 to 9. So actually this is the only week 1 assignment, that's why we have done in a very less time. We'll meet in the second week assignments. Thank you. So I will close the session.